Okay, we're going to start the last section in Chapter 1 here today with this video G 1.3. We've been talking about different ways of displaying quantitative data using graphs, but now we're going to get into how to describe quantitative data, not graphically, but sort of different calculations you can run with the numbers to describe the quantitative data. Okay, now the most common way to measure the center of a body of data is just the ordinary mean that you were probably taught in elementary school. Okay, it is very important that you become familiar with all the different symbols that are in AP statistics. Just a quick glance at the AP formula sheet and you will notice that there are a lot of different variables. And the variable that we use to represent the mean of a sample, okay, remember a sample is when you've collected a smaller group from a larger population and you've done that randomly. And then when you calculate the average of that sample, we use this variable with x with a little bar over top of it, and we actually pronounce it x bar. Okay, that represents the set of observations that if you were to add up all the values, obviously divide by the number of numbers, that gives you your average. And here's just a way of writing the formula. Now, this formula is actually on the formula sheet, but how it looks is it looks like this, okay? And so you see this Greek letter of the alphabet, it's pronounced sigma, and what it represents, it means to sum or add all of them up. So when you see this sigma symbol in front of an x sub I, it means to add up each of the individual values in the data set. So take the first observation x1 plus the second one x2, etc. And once you've summed them up, then obviously divide by the number of numbers. Okay, so that symbol right here simply means sum. Okay, now the mean of a population uses that symbol. I think we said that it's pronounced x bar. I think we already wrote that up above here. But another common measure of center is what we would call the median. Okay. Now you'll see how even though these are both ways of describing like the most typical value in your data set or sort of the center of it, how these are also different from each other. Okay, and we'll talk about that here in just a minute. The median describes essentially the midpoint of your distribution. Okay, the median is the midpoint of your distribution, and it is the number that half of the observations are smaller and the other half of the observations are larger. Okay, now to find the median of a distribution, what you have to do is you have to arrange all of your observations in order from smallest to largest. Okay, and something that's worth noting here is if the number of observations is odd, okay, so if you have an odd number of observations, let's say 5 observations, 1, 2, 3, 4, 5, then the median would just be that center value. Okay, however, if the number of observations are even, then there's not a distinct middle value. Instead, let's say you have 4 values. It kind of feels like the center is just right here in between. Well, then the median is the average of those 2 centered observations. So what this means is your median value could be a value that's not actually one of the values in your data set because it's the average of the middle 2 if we're talking about an even number of numbers. Okay. Now, here's where a big difference comes in between mean and median. They're not always really close to each other in value. Okay, you'll see this here a little bit with this example. This data represents the commuting time in minutes that it takes for 20 randomly selected New York workers to drive to work. Okay, and sorry that this data kind of goes down the page here a little bit, but we know that we would add all of those up. We would divide by 20 if we were going to do the average. Okay, we would add them all up, we divide by 20, and I'm just going to give you here that the average would be 31.25 minutes. Okay, If we were to calculate the median, we would need to first rearrange these numbers from least to greatest. You can see I kind of was trying to do that right here already for you. Okay, and then we would want to work our way from the outside in. We said there were 20 of these people, so there's an even number of numbers. That means the middle places us right here, 10 in from the left and 10 in from the right. So to get the median, I am needing to average together 20 and 25 for a median time of 22.5 minutes. Now, there's a pretty big difference between saying the center is 31.25 minutes and 22.5 minutes, okay? So what I want you to think about here between like these two answers for mean or median is the reason these are so far apart is because there's some larger numbers here. Okay, like there's one person that it takes 85 minutes for them to travel to work. Even these people here where it's taking an hour and a little over an hour, these are big numbers, okay? They might be outliers, possibly, but anytime you have an outlier, say, or several numbers that are either remarkably smaller than the bulk of the rest of the data, or certainly much larger than the bulk of the set of data, that is going to dramatically influence the mean. Okay, think about it. You throw in an extra number in there and divide. It's going to pull the mean towards the outlier. And so in stats, we say that the mean is not resistant to those extreme values or outliers. Okay, so not resistant to extreme values or outliers. The mean is not resistant. It will change dramatically. If I were to remove a few of these higher numbers and then recalculate the mean, you're going to notice it's not going to be quite as high as what we have here. Now the median, think about this, the median is not really influenced very much by outliers. If we were to remove, say, this 85 or this both the 85 and the 65, it would cause a shift, maybe over here where we would be looking at the median would be 20 minutes. Okay, it's not going to change a whole lot here. And it's really irrelevant that this number was a really high number. Okay, so what is resistant to extreme values or outliers is the median. Okay, the median is not heavily influenced by outliers. Now, I kind of calculated this median here, by hand, but there is a feature we will use a lot on the calculator. It will be helpful if you have your calculators really handy here today for us to talk through some of this here. If you put the data into your list 1, L1, and you would do that by pressing stat and number 1 for edit, okay? If you put this data into L1, and then you press that same stat button, but this time you want to go over to the calculate menu, you would pick option 1, one variable stats, and I think it'll ask you where your data is, and across from list you would want to say L1, and then it's going to just spew out all of these calculations. The very first calculation is the mean, which should be the 31.25, and if you continue to scroll down to the bottom, you'll see towards the bottom there's a number labeled MED for median, and that should match up with what we said our median was here. Okay? All right. So that's talking about measures of center. Typically 2 measures of center, mean or median. Let's talk about numerical ways of describing spread. Okay? The simplest way to describe spread is by describing the range. Okay? The range is nothing more than taking the maximum value minus the minimum value. Here's what some people get confused though. The range is a single number. Okay? The range is not you like listing, like if I say, I want you to read in your book tonight pages 21 through 30, you're not listing smallest dash largest. You are only reporting the single number. Okay? So the range in and of itself doesn't really tell you what the smallest and largest number is. It just tells you how many units the data set spans. Okay? Now, a measure of center alone can be misleading. Okay. So this is why we talk about spread. A useful numerical description of a distribution requires that we know both the center and the spread, and this is kind of building into why when we describe distributions we want to include all these things, center and spread. And so we're going to talk about another measure of spread other than just range is quartiles, and also what's known as an interquartile range. Okay, quartiles really build off of the idea of medians, okay? And once you have your median, it splits each half of the data into another half, and that's where we get the quartiles. It says to arrange the observations in increasing order, locate that median value. The first quartile, known as Q1, is the median of the bottom half of your data, and the third quartile, known as Q3, is the middle of the upper half of the data. And when we talk about an interquartile range, the interquartile range is the range of, or the difference, the spread between Q3 and Q1. Again, it is a single number, okay, a single number here. So let's say that we have these two sets of data here. We have all of McDonald's beef sandwiches, and then it looks like maybe we have like their chicken and fish sandwiches listed, and the number of grams of fat in each of these. Okay, so two different data sets here. The question is find and then interpret the interquartile range for each of these two data sets. Okay, so I went ahead and I listed along the sides. I did this vertically, but I listed along the sides the grams of fat from smallest to largest. Okay, and if we found the median for the beef sandwiches, okay, the very middle would be right here in the middle between the 26 and 26. So if we average 26 and 26, we get 26. Okay, now for Q1, that is the middle of this bottom half of data, which also has 6 values in it. So that means Q1 would be right in the middle of 19 and 23. If you add 19 and 23 and you divide by 2, Q1 is 21, and then Q3 would be 29 grams. Okay, I'm going to go ahead and do the same thing over here with the fish and chicken sandwiches here. This, though, has an odd number of values in it. So that means the median is right here at 19 grams, okay? But then Q1, I'm going to have to average 14 and 16 to get 15 grams, and Q3 is the average of 22 and 27 to get 24.5 grams, okay? So here I have Q1, the median, and Q3 for each data set. This is asking us to come up with the interquartile range, okay? This is a single value that represents how much does the middle 50% of the data take up, okay? And so what we would do here is we would simply take 29 minus 21, and we would get the interquartile range to be 8 grams. The middle 50% of the beef sandwiches, their fat gram content, spans 8 grams. And then for the fish and chicken, it spans 9.5 grams. Okay, I will tell you, and I did these by hand here, but again, if you were to enter the beef sandwiches, say, into L1, the fish and chicken sandwiches into L2, and one at a time, press one variable stats, that was second, and the calculate button. You'd have to first tell it L1 data, and if you scroll all the way to the bottom, okay, all the way at the bottom, you're going to see it identifying Q1 and Q3. Okay. What the calculator doesn't straight out tell you is the interquartile range, but it gives you Q1 and Q3. You can pull those numbers and you just have to know to subtract them to get the interquartile range. You go back and repeat the same thing, only when you press one variable stat, make sure you change it so that it's doing it with the data in L2. Okay. Okay, very, very important. This is huge. Identifying outliers. Okay. This is a formula that you definitely need to make sure that you commit to memory, okay? In addition to serving as a measure of spread, the interquartile range is used as part of like a rule of thumb for identifying outliers. Like a lot of times we've just been looking at these graphs and we've been saying, oh, that dot that's kind of all the way off to the side, that kind of looks like an outlier. Well, in stats, there is a specific way that we could really say for sure whether something is an outlier or not. You can't just say it looks like an outlier. You have to calculate this before you call it an outlier. Okay, and so this is comprised of two parts. You're going to create a lower fence boundary and an upper fence boundary. And any pieces of data that are outside of those fences, smaller than the lower fence or bigger than the upper fence, those are considered outliers. Okay, here's the formula, and this is what you will need to commit to memory. Q1 minus 1.5 times the interquartile range is the lower fence, and Q3 plus 1.5 times the interquartile range is the upper fence. Okay, all right, so let's take a look here at this example here, and then this will be a good stopping point here for us. Okay, so the question is, were there actually any outliers in the New York commuter data set? Okay. Now I'm going to scroll back to that so you see what we're talking about here. We're not talking about the grams of fat here. We're talking about this data set right here. Okay, so what we would do is we would put all this data into L1. Okay, we're going to put all that data into L1 on the calculator, and that's what I'm describing right here. I'm saying enter it into L1, go ahead and run one variable stats, that's by pressing stat calculate, scroll all the way to the bottom and grab the Q1 and Q3 values. These are the two values that should be showing up on your calculator screen. Okay, when you have those two values for Q1 and Q3, okay, the first thing we need to do is to figure out, well, what is the interquartile range? That's Q3 minus Q1. That would be the 42.5 minus 15. That would be 27.5. Okay, then to set up my lower fence, the formula is, I'm just going to write underneath this, Q1 minus 1.5 times the interquartile range, and then the upper fence is Q3 plus 1.5 times the interquartile range. Okay, whether you think this is tedious or not to show this work right here, the AP graders will dock points if you do not show this. You cannot do this work on the calculator, even though this seems like a simple calculation for sure. If you just write down, hey, this one's an outlier, they have no idea if you're just like guessing or if you actually did a calculation to show that you know this formula and that this is what's used to say whether something is in fact an outlier or not. Okay, you have to show this work. Okay, so that sets up our lower fence. Our lower fence is negative 26.75. Remember, these are commuting times. I'm going to label that minutes. Upper fence 83.7. Oh, I messed that up. It's 26.25. Negative 26.25. Upper fence 83.75. Now, granted, having a negative commuting time to work makes no sense, but that just means that none of the low values in the data set are considered to be outliers, because it would have to be a number smaller than negative 26.25 or any commuting times larger than 83.75 would be considered an outlier on the high end. So let's go back and look and see if there were any values bigger than 83.75. Okay, let's see here. I had them rearranged. Right there. 85 minutes to work. Okay, so we're going to go ahead and say, it was asking, were there any outliers? We're going to say, yes, the time of 85 minutes is an outlier. Okay, and all of our work there supports that conclusion, so we are good to go there. Okay, lastly, what's called a 5-number summary. Okay, these are basically the last 5 values that are at the very, very bottom of the screen when you run one variable stats. Okay, in essence, the mean and the max, those values all by themselves don't tell us a whole lot about the distribution. The median and the quartiles, don't tell us a whole lot about the ends of the distribution. So if we want to get like a quick summary of the center and the spread, then we want to be able to combine all 5 of those values together into what we call a 5-number summary. And the 5-number summary is this: the min value, first quartile, the median, third quartile, and the max, or the largest observation. And these are the very 5 last values listed when you run one variable.